being disassembled in a day's time. Now, the other part about a red blood cell, the structure of the red blood cell, the surface of it is going to play a part in our blood type. How many of y'all know your blood type? I used to. I don't remember it anymore. Okay? The other thing about the red blood cell, the red blood cell is going to have to make it to the capillary beds because it's at the capillaries where exchange is going to take place. Now, when we get down to the capillary beds are extremely small. They're microscopic, okay? Don't even know how many we have within our bodies, all right? So, at that point where we get to a capillary bed, in that capillary bed, arteries meet the veins. Okay, just try to keep, don't write it down. I'm giving you guys, I'm just trying to give you some background information as we move forward. Okay, so for that red blood cell, by the time it gets to the area where an artery is going to meet a vein, that red blood cell is having to pass through single file. So that means at that capillary bed, the blood that has been brought to it, that red blood cell, it's actually getting squished, squeezed, and everything else. In doing that, it's releasing the oxygen, okay? And then the stuff that's been produced at that tissue, and in this vein side, if there's CO2 that the red blood cell will pick up, it'll pick it up. Otherwise, the other bits of CO2, the other CO2 gases, they're going to have to be taken care of a different way. And they're going to make their return back to the heart. And then that red blood cell doesn't have any oxygen, will go into the pulmonary circuit, return to the left side of the heart to get pumped back into the arteries. Okay? So what this means is that red blood cell, it is going to have to be squeezed and squished through at the point of those capillaries. It undergoes a lot of stress. We have to make sure that it's very durable to do this. So the makeup of that red blood cell allows it to be squished and so forth. Now, when we think about this squishing, it is squeezing the oxygen off of it, okay? So that the oxygen can move into the tissues that are fed by that capillary bed. Does that make sense? Okay? So this gas transport is the major function. We have an increased surface area because of it being biconcave, looking like a donut. We get the loss of the organelles, and that's going to make it easier for materials to be carried by that red blood cell. Over 30% of the cytoplasm in a red blood cell is hemoglobin. So a large portion of what that red blood cell did in its first few days of life was give rise to the hemoglobin, because in one red blood cell you can have over 200 million hemoglobin molecules in one red blood cell. Over 200, well, I'm talking bunches of hemoglobin molecules, because their job, pick it up, drop it off. And they want to do that with as much oxygen as possible. is their major concern. So what does that do about the carbon dioxide? Because I know that before I learned about it, I had the idea that the red blood cell, the oxygen that it picked up in the lungs, dropped all that oxygen off at the tissues, picked up all, all that CO2, returned to the lungs, we breathed it out. No, that's not what happens. The oxygen that is going to be dropped off at the tissues, the red blood cell is only going to drop off as much oxygen as that tissue cell needs for metabolic needs. So if the hemoglobin molecule can carry 4 oxygens, it may only need, at this tissue right here, to drop off 2. It'll hang on to the other 2, make its way back to the pulmonary circuit, pick up 2 more and be back to 4. Or maybe pick up 1 and be at 75%. Does that make sense? So that tells me that the carbon dioxide, and where does my carbon dioxide come from? What is producing the carbon dioxide in our bodies at the cellular level? Because that's where we're at. We're at the cellular level of that oxygen being dropped off. Cellular respiration, which involves the Krebs cycle, okay? And we're in mitochondria, okay? So that CO2, if that tissue is being metabolically active, it is producing carbon dioxide as a waste. We do need to pick up that carbon dioxide needs to leave that area of the tissues, make its way back to the lungs to be breathed out. But it doesn't have to be on a red blood cell. It can simply move into the blood stream. Now that says that the CO2, it can move into the bloodstream, but in the bloodstream, there's water. And if I take CO2 and I move it into the bloodstream, and there's water in the bloodstream, it's going to dissolve in the water. What does that create? Does anybody remember? And it's carbonic acid. Now wait a minute. If I get the carbonic acid in the bloodstream, what have I now done to the pH of the blood? I've affected the pH, meaning if pH should be roughly 7.4, if I've increased that, do I go up or down? Down. I go down, okay? So if it goes down, there has to be something that will offset that in the blood, because the body is going to maintain the pH of the blood very tightly. Okay? The last thing that the body wants is for the pH of the blood to be incorrect. So the body is going to have to buffer the CO2. All right? So what we're going to find that in the cytoplasm, we're going to have something called carbonic anhydrase, because the CO2 that gets formed and has to leave those cellular tissues, okay? The CO2, it can travel in 3 ways, all right? The CO2 that gets produced at that cellular level can travel in 3 ways. By way of the bicarbonate ion it can travel on a hemoglobin in this red blood cell. So by way of the bicarb, by way of the hemoglobin, are actually dissolved in the plasma of the blood. We really do not want it traveling in that fashion. But there is a little bit that will get dissolved in the plasma of the blood. So, that tells me of these three ways, the majority is going to travel in which way? The bicarbonate ion. Isaiah, over here. Now, the bicarb ion is going to be produced when CO2 and water combine. Okay? The bicarb ion gets produced when CO2 and water combine. And they're going to combine to form carbonic acid. And we have to take care of that. So what do we get? Carbonic anhydrase becomes very important. So if I take CO2 plus water, okay? Should have brought my board out, I'm sorry you guys. All right. In the presence, okay, if we get the CO2, if it moves into the bloodstream, if it combines with the water, we're going to see that in the presence of the carbonic anhydrase, all right, this is going to form our bicarb ion, okay? All right? Now, this reaction that's taking place, this reaction is now reversible. All right? And what that's going to give us, once we have this H2CO3, the bicarb ion, it will give us an H plus and I want to say minus. Yes.
Yeah.
And it simply becomes reversible so that we can transport the CO2 in the blood. And we don't have to use the space in the red blood cell to carry CO2.